Okay, at this point we're just going to formalize the informal definition of semantics that we just looked at. So this is what's captured by definition 719 in the textbook. So suppose we have some formula A, and we have an interpretation and an assignment. So I sub A is an interpretation for A. So it specifies the domain, and it specifies a relation of the appropriarity for every predicate symbol in A, and it specifies an element of the domain for every constant symbol in A. Then in addition, in order to assign domain elements to the variable symbols, we have an assignment, sigma I sub A. The question then is, what is the truth value of the given formula A under this interpretation and this assignment? So as in the propositional case, we'll denote the truth value by this little function, little v, and it will in general have this subscript sigma sub I sub A. We'll simplify that in a moment. So the truth value, v sigma sub I sub A, of A it's going to be defined, of course, by a recursion that mirrors the recursion that defines the syntax of our formulas. And to make things simple, we're going to denote v sigma sub I sub A simply as v sigma. So again, the recursion will follow the same structure as our recursive definition of syntax. So the first case, simple case, is that of a leaf, a simple leaf. In other words, the case where A is an atomic formula. So in that case, A has the form, say, P sub K, C1 up to Cn, where these Cn's are either, I'm going to rewrite this as T1 through Tn, because these are really terms. It's better to call these things terms. So pk is an n-ary relation symbol, and each of these T1s, T1 through Tn, is either a constant symbol or a variable. Symbol. Okay, then what is the truth value of such a formula A? We'll say that v sigma of A is T if and only if the elements of the domain that these terms denote, that n-tuple of elements of the domain denoted by the terms T1 through Tn, belongs to the n-ary relation denoted by the predicate symbol pk. So in other words, the truth value of the formula is T if and only if d1 through dn the elements of the domain denoted by our terms, the n-tuple of those elements of the domain, belongs to the n-area relation Rk. So Rk is the relation assigned to Pk by the interpretation and these di's di is the domain element that is assigned to ti, and what is it that assigns that domain element di to ti? Well, that depends on whether ti is a constant symbol or a variable symbol. The domain element will be assigned to ti by the interpretation I sub a if ti is a constant symbol and by sigma sub ia if ti is a variable symbol. Okay? That's the simple case where our formula is merely an atomic predicate. So if A has the form of a predicate symbol followed by the appropriate number of terms in parentheses, then its truth value is true if and only if the domain elements assigned to that n-tuple of terms forms an n-tuple that belongs to the n-area relation assigned to the predicate symbol. Okay. And what is it that assigns these domain elements to the respective terms through T1 through Tn? That depends on whether a given term Ti is a constant symbol or a variable symbol. If it's a constant symbol, its meaning, if you like, is assigned by the interpretation. And if it is a variable symbol, then its meaning is assigned by the assignment. That is, the assignment assigns to Ti a particular element of the domain. So that's the basic case where our formula is just a leaf. Then we just continue with the other cases in our recursion. So if, for instance, we have a negated formula, so suppose A is of the form not A1, well then of course its truth value is going to be T if and only if A1 has the truth value false. Negation means, of course, the same thing as it did in the propositional case. And the same is true for all of the binary operators. So, for instance, if A is a disjunction, A1 or A2, then its truth value will be T if and only if either V sigma A1 has the truth value T or V sigma A2 is the truth value T. And of course the definition is similar for other binary operators. So it only remains to give the semantics of the quantifiers. So we'll say that Under our interpretation and our assignment, the universally quantified formula for all x a1, say, will have the truth value t if and only if, when we take the same interpretation and the same assignment, except we consider modifying the assignment that is made to the variable symbol x, the truth value of a1 comes out to be t, no matter what domain element d we reassign x to. Okay? So in other words, the universally quantified formula for all x a1 has the truth value t if and only if a1 has the truth value t, no matter how we reassign the domain element that x denotes. And when we do this reassignment, of course, we leave the other variable symbols alone. They are simply assigned to the domain elements that the original assignment sigma assigned to them. All we're doing here is changing sigma so that it assigns x to the value d, the domain element d. And if, no matter which element of the domain we assign to x, the formula a1 comes out to have the truth value, then we say that the universally quantified formula for all x a1 has the truth value t. That's just a more formal version of the informal semantics that we defined in the previous video. And of course, the clause for the existential quantifier is similar. The truth value of there exists x a1 is going to be true if and only if the truth value of a1 comes out to be true for some element little d of the domain to which we reassign x. So in other words, the existential quantifier, there exists x a1, has the truth value true if there exists some element little d of the domain, such that when we stipulate that x be assigned to that domain element little d, but all of the other variables are left alone, they're assigned to the values that the original assignment sigma assigns them to. Then if there does exist such a value little d, such that reassigning x to little d makes the formula a1 come out to be true under our assignment and interpretation, then this existentially quantified formula, there exists x a1, has the truth value true. Okay, so again, the universal formula is true if for all elements d that we might assign to the variable symbol x, a1 comes out to be true. The existential formula has the truth value t if and only if for some element little d of the domain to which we can reassign the variable symbol x, a1 comes out to be true. So as long as a1 comes out to be true under some assignment of a domain element to x, the existentially quantified formula is true. That completes our formal definition of the truth value of a first order formula. Now, notice that if all of our variables are quantified, then we apply either this clause or this second clause to each variable. So in the case of every variable x, we're considering all sorts of possible reassignments of values to x. So the value that sigma originally assigned to x is immaterial. If all occurrences of x are bound, then the semantics is just going to depend on what happens when we consider reassigning the value of x. So the original value assigned to x by sigma will be immaterial. That is reflected in theorem 720, which we won't bother proving. And that says if A is a closed formula, so in other words, it doesn't contain any free occurrences of any variables, then the original value assigned to any of its variables by our assignment, those original values are immaterial, because in determining the truth value we consider all possible reassignments to those variables. So the assignment itself has no effect on the truth value, because we just consider all possible reassignments to the variables occurring in A. So the truth value of A under our interpretation and our assignment, in fact, does not depend on the assignment at all. So we can therefore, if A is a closed formula, simply denote its truth value V sub IA of A, without mentioning the assignment. Okay? Because again, if all of the variables are quantified, then we just consider possible reassignments to all of those variable symbols. So whatever value they were originally assigned under some assignment is immaterial. Let's go through a quick example. We earlier looked at this formula. This was a closed formula for all x p ax. Under three possible interpretations. And again, because this is a closed formula, its truth value will only depend on the interpretation. We don't have to consider any assignment. The first assignment had as its domain the natural numbers, had as the binary relation assigned to the binary predicate symbol the ordinary less than or equal to relation on the natural numbers, and the one constant symbol A was assigned to 0. So what does this mean? We said that under this interpretation, that formula should have the truth value true, because it essentially means that for every natural number x, 0 is less than or equal to x. And in fact, that is true. If we work it out maybe in a little bit of detail, we know that the truth value of our formula sorry, this should have just been a parenthesis here because this is a triple. So the truth value v sub I1 of, for all x, P(ax) should be true if and only if the truth value of P(ax) is true under the assignment of any domain element D to the variable symbol x. In other words, if and only if 0 is less than or equal to D for all D in the natural numbers. And that is, of course, true. That was one interpretation that we considered. Another was I2, where, let's see, again the domain was the natural numbers, and again the binary relation to which our binary predicate symbol was assigned was the ordinary less than or equal to relation. But in this case, the constant was assigned to 1. So in this case, the truth value of our formula for all x P(ax) is false, because suppose we consider assigning to x the value 0. Then P(ax) has the truth value f. Because, of course, 1 is not less than or equal to 0. Or if you like, the ordered pair 1, 0 does not belong to our binary relation less than or equal to. So there exists an assignment of an element D of the domain to our variable symbol x, such that P(ax) has the truth value f. And that means that the universally quantified formula cannot have the truth value t, so its truth value is f, just as we said. And finally, I3 was the case where the domain of the interpretation was the integers. The relation was still less than or equal to, and then we went back to letting the constant be 0. But here again, the truth value of the formula is f. The truth value of our universally quantified formula is f. And for that, we just have to consider, for example, assigning to x the value -1, which is in our new domain, which is the integers. Of course, 0 is not less than or equal to -1. So under that assignment to x, the atomic formula has the truth value f. Therefore, according to our formal definition of the semantics of the universally quantified formula, that universally quantified formula has the truth value f. Let's wind up this video just by mentioning one other result, another one that we won't bother proving. It follows pretty immediately from the definition of semantics that if A is a formula with free variables x1 through xn, and if I sub A is an interpretation for A, then the truth value of A under some assignment sigma I sub A will be true if and only if the truth value of the existential closure of A is true. Okay. Our formula, our formal semantics says that this existentially quantified formula will have the truth value t if and only if there are elements of the domain to which we can assign these free variable symbols that make the resulting, that make the formula A come out to have the truth value t. But that is precisely what we're saying here. Suppose that there is some assignment of values to those variable symbols that makes A come out to be true. That is the case if and only if the formal semantics say that the existential closure has the truth value true under this interpretation. And of course, because the existential closure is a closed formula, its truth value depends only on the interpretation and not on any assignment. That's part one of the theorem. Part two is a similar statement for the universal closure. So if V sub sigma I A of A is true for all assignments, sigma sub I sub A, well, that is the case if and only if, under the interpretation I sub A, the universal closure of the formula A is true. And again, that's a pretty direct consequence of our definition of the formal semantics of first-order logic. So that completes this video that gives the formal definition of semantics and some of its straightforward consequences in terms of these theorems. Now, when we were dealing with propositional logic, we also talked under the heading of semantics about notions of satisfiability, unsatisfiability, and logical consequence. And those notions will carry over to first-order logic. But we'll address that in the next video. So I'll see you there.